If we want to understand what's going on around the event horizon, as you get close to the event horizon of a black hole, we have to dramatically change our conception of space and time. And so buckle up, this is going to get a little bit weird. But let's start with something not weird, something fairly common, and we'll start building the language that we need to talk about the more advanced theory. So this is about the principle of relativity. Now, the theory we're going to get to is the theory of relativity. The principle of relativity is part of that, but this is an older idea. This is not new. This is not new to understand black holes or anything. This is just the idea that when we observe things, our observations can differ in terms of how we would describe them in space and time, because we might be moving differently because we're located in different locations. If you want to describe an event, anything that happens in the world around you, you could give it four numbers, four coordinates, an x, y, and a z, so the three space dimensions, and so that's its position in space, and also a time. When did it happen? So you're describing its position and its time. And those four numbers would describe that event in your frame of reference, from your perspective. Well, I could describe the same event as you, and if I'm moving differently, like if you're viewing it from a train and I'm viewing it from the ground, then our four numbers don't have to be the same. This is the principle of relativity, that our observations of position and time are relative to one another. Okay, so this dates way back, goes back to Galileo. Galileo understood that there was this principle of relativity. And so the main idea here is that the laws of physics are all the same, but we can still perceive events, measure them with different coordinates, just based on our frame of reference. Okay, so not incredibly, nothing incredibly weird going on here. It is very matter of fact. So let's take a quick example just to make sure this is very clear. A train is passing by. You're on the side of the road. Your friend passes by on a train. We'll call the train passing by the event. So that's the event that happened. The train passed by. From your perspective, your friend is moving and you are stationary. From your friend's perspective, the opposite is true. So in your reference frame, your spatial coordinates are not changing. They're the same numbers, the same set of numbers, right? You would say I'm at, let's say you put your coordinate system on yourself. You were at the origin of that coordinate system. X, Y, Z coordinates are 0, 0, 0, and they're not changing. As time goes on, the 0, 0, 0 doesn't change. But in your friend's reference frame, they have a different coordinate system, right? They have a different set of X, Y, and Z. And so in your friend's reference frame, then you are moving by them rather than them moving by you. And so for that reason, you measure yourself as stationary with 0 speed. They would measure you with whatever speed you measure the train. That's all the principle of relativity is saying, that you can disagree on speeds of things because of this relative reference frame. All right, so it's a little challenging to get the math all straightened out, but there's nothing weird about it. It's just a difference in perspective. So now we'll introduce Albert Einstein. He's really the star of this show this week. It was his work that gave us the theory of relativity that we'll need. And we're going to start out with this special theory. Now, special refers to the fact that it's only applying in specific requirements are met. And we'll get into that a little bit more when we cover the general theory, which is more broad, which covers everything. But he started out with the special theory. He started out small, and this was in 1905. He postulated that light always has the same measured speed independent of the observer. So take a second to digest that and compare back to the previous slide. Principle of relativity tells us that different people can get different results for the speeds of things as a result of how they're moving, right? I measure the ground to be stationary and the train to be moving. You measure the train to be stationary and the ground to be moving. Well, Einstein's directly challenging that as it pertains to light. He says light always has the same measured speed. So if I'm in a train measuring it, if I'm on the ground, I get the same number. It's independent of the observer. So at first you might look at the principle of relativity and say, oh, well, that's obviously wrong, we can move on. It's not intuitive at all. Well, if you did that and you threw this away, you would be wrong, because this has proven to be true. Light is very different than anything else, and it does always have the same measured speed that is independent of the observer. And the theory that evolved from this, and the consequences of that we'll get into in a minute, is known as the special theory of relativity. And it applies whenever the observer moving is at a constant speed. So as long as the observer moving is at a constant speed, this theory applies, and such an observer is called an inertial observer. So the language here, don't get too don't worry too much about the terminology. As long as something's moving at a constant speed, the special theory of relativity applies. So let's go back now and say, why did he come up with this? Why could anyone come up with a new theory that directly contradicts something that was well established, like the principle of relativity? And the idea came from thinking about electricity and magnetism. That doesn't seem like there would be a relationship there. But if you go back to the late 1800s, early 1900s, the question of what is light was very, very hot topic. And it was recently discovered in that time that light was an electromagnetic field, that an electric field oscillates, causing a magnetic field to oscillate, which causes an electric field to oscillate, and that propagates forward. So light was really an electromagnetic wave. And what Einstein did was he imagined riding along that light beam and asking, what would you see if you were riding along at the speed of the light wave? And what he concluded was that it doesn't make any sense to ride along at the same speed as a light wave, because if you looked at the light wave, you wouldn't see the fields oscillating because you were moving as fast as the wave. And so then the laws of physics would have broken down, because there would be no reason for the magnetic field to be there if the electric field wasn't changing, and no reason for the electric field to be there if the magnetic field wasn't changing. And so he came to a paradox that he couldn't resolve, or that really had to be resolved in one way or another. Either you said the laws of physics describing electricity and magnetism were incorrect and needed to be updated, or you said that you just couldn't do this. You could not ride along a light beam. And Einstein chose that one because he believed the equations of electricity and magnetism were correct. And he said, well, then the only alternative is that you cannot do this experiment. You could not ride along at the same speed as light. And then he simply asserted that that must be a law of nature. No one can travel as fast as light. It is the ultimate speed limit. So from there, he made this leap. Actually, I'll take the highlighting off. All reference frames are equally valid for describing the natural world, and hence all observers must measure light to have the same speed. So if no one can travel fast as light, but you also believe that the laws of physics have to be the same for all of us, then the only conclusion you can come to is that everyone has to measure light with the same exact speed. You can't catch up to it at all. No matter how fast you want to go, you cannot catch up to light. It's always moving away from you at the same speed. Hard to believe that that's true, but it has proven to be true. All right, so let's try to understand this, because this is a tough thing to understand. Imagine your friend is on a bike going 25 miles per hour. If you run after the bike at 10, then it would be moving away from you at 15. Okay? If you got in a car and drove at 40 miles per hour, you'd eventually catch up with the bike. This is how relative speeds would work, at least according to our everyday experiences. What Einstein is saying is that light does not follow this rule at all. When you speed up, it seems to speed up too. So it's always moving just as fast relative to you. There's nothing you can do about it. Okay, so you might not believe that this is true, and you certainly don't have any intuition for why this is really true. You're sort of going on Einstein's intuition about the laws of physics here, but I can promise you that it has worked out to be true. So let's just go with it and think about the consequences. What are the consequences of the speed of light being the same for everybody? The two main consequences are time dilation and length contraction. So sort of more straightforward way of saying that is that for moving observers, time runs slowly. The ticks of a clock are slower for people on moving reference frames, moving relative to the things that they're measuring, I should say. Because the question of who's moving, are you moving or am I moving? Well, it's, are you moving relative to the things that you're observing? If you're moving relative to the things you're observing, then your clock's going to run slower than someone who's at rest relative to those events. Similarly, the length between things, if you're moving relative to them, contracts. It gets smaller. So the most helpful way for me to remember how this works is if you imagine someone getting in a spaceship and traveling off to some distant star, then for you sitting back at home, you are at rest relative to the two places, the Earth and the star. You're just sitting there on Earth, the star's just sitting there in space. So you are in the rest frame of reference. The person in the spaceship, on the other hand, is moving relative to the Earth and the star, so they're in the moving frame of reference. For that person, in the moving frame of reference, time will slow down and length will contract. So you might measure it takes years for that person to travel to that star and back, but for them, it might happen in months or days or seconds, depending on how fast they were going. Because their clocks have slowed down, so less ticks of the clock would have happened, and the distance that they seem to have traveled had contracted and gotten a lot smaller. You say, well, that star is 4 light years away, and the person on the spaceship says, no, that's only like a couple of miles away. Again, I don't expect this to make total sense to you immediately, but if you assume that the speed of light is constant and you work out the mathematics of that, as Einstein did back in 1905, you find that our time differs and our measurements of length differ. And they differ in this way, where if you're moving relative to the events, time slows down and lengths get smaller. Very strange, but that's the way it happens to work out. Okay, so that was the theory of special relativity. It gives us time dilations and length contractions. Our concept of space and time is now changed because the speed of light is a constant. It's the same for everybody. So now we agree on the speed of something, we have to differ in our measurements of space and time. Whereas with the original principle of relativity, we agreed on how to measure distances and times, but we could disagree on how fast things are moving. This is sort of like flipping that on its head. But that only covers people moving at constant speed. What we said earlier were inertial observers. In gravity, things accelerate. And so to really understand gravity and to have a more advanced theory of gravity, we need to be able to account for motion that is accelerated, speeding up, slowing down. And for that, Einstein needed to expand his special theory of relativity. And it took him about 10 more years, actually closer to 11 more years, to work all the details out of that theory, which is now known as the general theory of relativity. And it covers not just inertial observers, but also non-inertial observers, people moving at non-constant speeds. And the key idea that sort of unlocked this theory for him is the equivalence principle. And the equivalence principle states that free fall is equivalent to having no gravity at all. So he made a connection here that allowed him to understand this way that space and time had to change in order to account for things that are accelerated. I don't expect that to make sense immediately, but we'll try to unpack that next. So what does this equivalence principle really mean? Well, if you think about it in terms of making measurements, doing an experiment, and that's what the way Einstein thought about these problems was in terms of doing experiments, because one of his central tenets was that the laws of physics had to be the same. And so you could confirm that by doing an experiment. And whether you're in an accelerated reference frame or not, you could do an experiment. And the laws of physics would have to be the same. But the result of the experiment would not have to be the same, because your reference frame is different. Now, the laws of physics would be the same, but the result of the experiment would not be the same. And let me give you a quick example of that. Let's say you are in a car, right? And you're a passenger, you're not a driver, but the person is driving along at constant speed. And you have like a tennis ball in your hand, and you throw it up and down, throw it up and down. The ball is going to go up and come down, just as if you were standing on the ground, not in a car. If you were doing that experiment and your driver speeds up, like floors the gas and goes forward, and you throw that ball up in the air, it's probably going to hit you in the face. It's not going to go up and come straight down, because as you throw the ball up, the car accelerates forward, and the ball is now not moving with you. It's not being pushed along because like you are being pushed by the seat of the car. And so the point is, the result of the experiment would be different if you were in an accelerated frame of reference. All right, so what does the equivalence principle say? Let's go back to that. Free fall is the same as no gravity at all. That means if you were in a reference frame that was freely falling to the ground and you performed an experiment, it would get the same exact results if it were performed when there's no gravity at all. So you were in 0G. So let's look at these pictures here where a person is standing on a scale in an elevator. And the purpose of the scale is essentially measuring what you're pushing down the scale, which would have to do with gravity, right? If you were in a 0G environment, you would be weightless. You would not weigh anything. If the elevator is just hanging and not moving, so there's no arrows indicating motion here, so this is just sitting there or hanging there, you're on the scale, you would weigh your normal weight. As the elevator falls down, right, so it's accelerating down, you're speeding up going down, then gravity is doing some of the work pulling you down, but the floor is also accelerating away from you, and so you would appear lighter than normal. If the elevator pulls you up, you're going to appear heavier than normal because you're working against gravity, and the scale is working against gravity to push on you. Then if you cut the scale, what would it read? Well, then you're falling at the rate of gravity, the scale's falling at the rate of gravity, the elevator's falling at the rate of gravity, and so you would appear totally weightless. So these 4 reference frames are different. The experiment gives different results. This is your normal weight, you're lighter, you're heavier, and then you have no weight at all. Okay, so same experiment but different results. What the equivalence principle means is that free fall, which is this one, where you have no weight, is just like you were in empty space. So if you were in this box, right, and it was freely falling, and there was no windows and you couldn't see out, you wouldn't be able to tell. There's no experiment that you could do that could tell you whether you are freely falling to the ground or whether you just are out in empty space, just hanging out. All of the physics would be exactly the same for you in that frame of reference. All right, so let's take a look at this example here. This is 2 people jumping off a cliff. These little mental experiments here get kind of strange, but it helps. So the 2 people here jump off a cliff and are playing pass. All right, so if you prefer, imagine there's a big trampoline here at the bottom that they're going to fall safely to the trampoline. Now, as they're falling together. Gravity is working the same on both of them, and so they're going to accelerate to the ground at the same rate. The ball also will fall to the ground at the same rate. So in order for them to pass the ball back and forth, they just throw it straight ahead, right? And so in their reference frame, he's here, she's here. A moment later, he's here, she's here. And from their reference frame, they're just passing the ball straight back and forth to one another in straight lines. If you were watching this happen from the side, however, what you would see is that the ball took a curved trajectory. It left his hands here and arrived down here in her hands. It left her hands here and arrived down here in his hands. So depending on your reference frame, the ball either took this path or it took this path. So is one of the reference frames wrong? If you ask the question, did the ball take a straight line or a curved trajectory, is one of those answers correct and the other is wrong? Well, no. This is what relativity means. It means that your observations here can be completely different depending on your frame of reference. In each of these reference frames individually, it makes perfect sense what happened. These people don't feel like they're moving relative to one another, and so the ball is just going in a straight line. In our perspective, these people are moving relative to the ground around them, and so the curved trajectory makes complete sense. All right, so now let's come back to gravity out in space and think about orbits. So we've talked a little bit about this when we were covering orbits several weeks ago. And Newton first made the observation that orbits are free fall. So something in orbit is in perpetual free fall. And that was his big revelation that for him helped him reimagine what gravity was. That the gravity on Earth is the same as the gravity in space. That an orbit is like free fall. Okay. What Einstein did was to extend this idea and give a deeper understanding of what gravity really is. So we can say orbits are free fall that's caused by gravity, and free fall is the same as when there's no gravity at all. And essentially, that's what the general theory of relativity is telling us. Orbits are free fall that are caused by gravity, and free fall is the same as being with no gravity whatsoever. Okay, so now we have the theories of relativity. Our conception of space and time are going to be a little bit different now. Measurements of lengths and measurements of times depend on your reference frame, and accelerated reference frames are going to have to be treated differently than non-accelerated reference frames. And so what we'll do next in the third video is to explore the consequences of that and what it means for black holes.